Good morning. I am Egoy Manzano, Assistant Professor at the University of the Basque Country, and I will present now our studies of Alite Dissolution using Kinetic Monte Carlo simulations. Alite hydration is a very complex process, even if we use it as a model of cement hydration. To describe it, we usually refer to the dissolution calorimetry curve, which shows a dissolution rate that changes drastically with time. In some recent studies, Julian, Nicolau, and co-workers have tried to explain the whole hydration rate curve from the mineral dissolution theory point of view, without taking into account the nucleation and growth of CSH and portlandite. According to their work, the initial dormant period corresponds to the initial dissolution of a light with the formation of etch pits at the surface dislocations. Then the acceleration in the dissolution rate is due to the etch pit expansion, which increases the available dissolution fronts. The rate reaches a maximum and starts to decrease when the etch pits merge, because the dissolution fronts have reached a maximum and then start to decrease due to their coalescence. And finally, the rate continues decreasing as the dissolution fronts decrease and particles shrink. So the objective of our work is to study this proposed dissolution mechanism using Kinetic Monte Carlo simulations. For our simulations, we have developed Chimera, a Kinetic Monte Carlo code for mineral dissolution. We try to build a very general code to be available to reproduce all the phenomenology of mineral dissolution, and in particular, we introduce as a key point the chemical reversibility. So we have separated the dissolution and precipitation reactions at the mineral surface, and the net dissolution rate is the net result of both processes. So we can study the net dissolution depending on the equilibrium conditions between the solid and the pore solution. We tested our code with quartz, and we proved that we can reproduce very well the etch pit morphology depending on the crystallographic plane that is dissolving, as you can see in these left panels. And we can reproduce as well the experimental dissolution rates and their change with temperature, obtaining macroscopic activation energies in very good agreement with the experimental ones, as you can see in this right plot. So, even if Chimera can go down to the atomic scale, as I saw for quartz, we can have atomic resolution, we think that we had to build a coarse grain model for a light. There are experimental evidences that show that the alite surface is prehydrated even before starting dissolution, and the simulations that predict that the crystalline order is lost in such a prehydrated interface. So at the interface between alite and water, we won't have a perfect crystal lattice. Therefore, we coarse grain our system in a cubic crystal, also called coarse crystal. Each side of this crystal is basically a C3S unit. We can do this because the dissolution of alite is congruent, so we don't need to consider the dissolution of calcium and silicon independently. By looking at the bulk crystalline structure of C3S, we define that each side of this cubic crystal would be a cube of a side about 5 angstroms, and we would study a system of 0.1 micrometers, so 200 of these sides, and using periodic boundary conditions. Now, for each side, the dissolution energy barrier depends on the number of neighbors, and the higher the coordination of a site, the higher the energy barrier necessary for the dissolution. So to calculate the rate of dissolution reaction for each of these sites, we need the fundamental frequency, or this pre-exponential factor, and the dissolution energy of the site. We don't know these energy barriers, so we use the available experimental data to define them. Thomas calculated in 2012 a dissolution activation energy for a light of about 51 kilojoules per mole. So if we assume that the limiting step for the dissolution is the dislocation, opening, and creation of etch pits, then that would be the energy corresponding for a site with 4 neighbors. Then, for covalent minerals like quartz, it's usual to take a linear relationship of slope 1 to calculate the energy of the remaining sites. For an ionic material like alite, we think that the difference between sites could be lower, so we use a slope of 0.5 to define them. This changes completely the dissolution mechanism, as you can see in these two videos. So we have the same system with one dislocation in the center of the surface, and the covalent mineral dissolves by step retreat with almost a layer by layer dissolution process, while the ionic material, the ionic mineral, dissolves forming an etch pit with a pyramidal shape. So very different processes taking different energies. So we use the ionic set of energies, and we need now to define the fundamental frequency value. For that, we used the experimental data from Julian and Galuzzi, you can see in this plot, and we calculated the frequency value necessary to match the macroscopic dissolution rate at far from equilibrium conditions, where precipitation does not contribute to the net dissolution rate. That will be essentially fitting this purple point in the figure. And finally, we assume that the frequency and precipitation energy barriers are equal to their dissolution counterparts. With all this, we can perform simulations, for example, at different temperatures and calculate, as you can see in this left plot, the macroscopic activation energy from the slope of the dissolution rate versus the inverse of the temperature, essentially the Arrhenius relationship. And we obtain macroscopic dissolution energy of almost 50 kilojoules per mole, very close to the experimental one. Or we can also perform simulations at a given temperature, for instance, room temperature, and change the free energy difference between the solid and the solution, as you can see in this right side plot. Our simulations are again in very good agreement with experiments, and we can capture the rate, the dissolution rate close to equilibrium, the dissolution rate far from equilibrium, as well as the free energy critical difference when the rate changes from one regime to another. Now that we have a good model and good parameters, we want to study the dissolution mechanism of alite. I will show now some plots of the cumulative number of dissolved sites in a crystal, this upper plot, as a function of time, and the corresponding dissolution rate as a function of time as well. First, we have in this slide the difference between the ionic and covalent set of energy values. You can see how using the ionic set, there is an acceleration of the dissolution rate with time, because the etch pit opening mechanism implies an increase of the available dissolution area. That doesn't happen in covalent materials that dissolve almost layer by layer, and the dissolution front remains constant. So the acceleration of the dissolution rate in alite could be indeed due to the etch pit opening if the dissolution energies of different sites have close values, which in principle makes sense because it corresponds to an ionic material like alite. Now, if we increase the number of dislocations from 1, which was equivalent to 10 to the 12 per meter square, to 5 in the same system, we can see the acceleration period. We can see that the acceleration period time decreases and a linear dissolution rate is reached faster. As you can see in this video, this is due to the coalescence of the opening etch pits. The dissolution rate increases as the etch pit open and remain constant when they merge. With one dislocation, it takes longer time to reach coalescence through the periodic boundary conditions than with 5 dislocations. So, the coalescence implies a constant dissolution rate, and this is an important difference with previous interpretations, which propose a decrease in the rate when etch pit merge. And that's because the available area for dissolution also includes the lateral size of the etch pits and not only the dissolution front. So it remains constant after coalescence. So then, is there a mechanism that could explain, could be responsible of the dissolution deceleration? We think that the dislocation exhaustion could indeed explain it. So far we have simulated system with infinite dislocation, but that's not necessarily the case. Dislocation can be finite, and in the dissolution process we may reach the end of a given dislocation. Here you have video illustrating this case. It's the same system as before, but in this case the dislocations end at different depths from the surface. So when the dislocation ends are reached, the available area for dissolution decreases, and then the rate starts to decrease. The process is overlapping with the coalescence of the remaining edge speeds until all the dislocations have ended, when the mechanism essentially changes to a layer by layer dissolution. So overall, the consequence is a decrease of the dissolution rate when dislocation ends are reached. As a summary, first we have developed Chimera, which is a very powerful tool to study mineral dissolution, and is an open source code, so you can download it from this link and play with it and use it for your own research. Second, we have investigated the dissolution mechanism of Alite, and according to our simulations, the initial acceleration could be indeed attributed to the edge speed expansion, as proposed before. But then the decrease would be due to the exhaustion of dislocations rather than the coalescence of the edge speeds. The rate would decrease as more dislocations ends are reached, and we could even have a change in the dissolution mechanism from edge speed opening to step retreat when all the dislocations have been consumed. Now, as future work, we can use Chimera as well to study the effect of superplasticizers passivating the surface, see the effect of point dislocations in our crystal, different morphologies, try to compare with C2S and so on. There are plenty of possibilities now for Chimera. So I hope that you found this presentation interesting, and thank you very much for your attention.